Welcome everyone. My name is Brendan O'Neill, and I'm a solution engineer on Esri's nonprofit and global organizations team. And today we're going to be talking about remote sensing and machine learning. Just before we get started, if you have any questions that you'd like to share with me throughout the presentation, please just drop them in the chat. And I'm not sure how much time we'll have at the end for Q&A. But we can work through those if we do have some extra time. And just to kind of get started, really the aim of this presentation is to introduce you all to some of the fundamental concepts of remote sensing, and then look at some of those concepts of machine learning that might apply to remote sensing. So let's get started. Now, the whole reason why we kind of put this program together is because those of us in the conservation, development, and humanitarian aid space are really faced with some of the most complicated problems in the world. And the programs that we run address large communities, and they across vast geographies. And on top of all this, we're really challenged to do more with less. I think that's true for all of us. So in order to kind of keep up with the pace of these problems and to make headway into addressing them, we really need to look to other technologies outside of perhaps the traditional ones that we've implemented for the monitoring and evaluation space. One of the tools that I think is very promising for monitoring evaluation is that of remote sensing. And just to level set, remote sensing is really the methodology of measuring energy that's either been emitted or reflected from the Earth's surface. So we have kind of two different types of remote sensing. One is passive remote sensing, where really we're just absorbing or we're measuring energy that's reflected by the Earth from the sun, or that's naturally emitted from those physical features on the Earth. The other is active remote sensing. You can think of things like LiDAR or radar for those sensor types. And what's really important in remote sensing is this idea that energy that's either reflected or emitted is reflected or emitted across this electromagnetic spectrum. So humans were equipped with our own set of sensors, one of them being our eyes, which is focused on the section of the electromagnetic spectrum that we see visible light in. However, different objects on the Earth reflect energy at different frequencies. Some of them we're unable to detect with our ears or eyes or our touch. And this is a really important concept because it allows us to actually measure things that we might not actually be able to see with our native eyes. And foundational to remote sensing is this idea that different objects on the Earth reflect energy in different ways. So it's this idea of spectral signatures. And much like our own signatures, where we can use them to identify who created them, we can do the same thing with spectral signatures. So here we have an example where we're looking at bare earth, vegetation, tin roof, and thatch roof, as we can see in the image to the left. It's color-coded. And at the bottom of the x-axis there, we can see the different frequencies of the electromagnetic spectrum. So we see blue and green to the left, and then red and near infrared to the right. And we can see that there's difference in these spectral signatures across these different frequencies. So for example, a tin roof is going to reflect energy very differently than bare earth or a thatch roof. And we'll dig into this example a little bit later. Now, there are a lot of different sensor platforms out there, from satellites to your iPhone, really. And they all have different advantages or disadvantages. So for the example of satellite imagery, we send these satellites up to space. They're usually there for a while, capturing imagery, and then they're archived in these imagery archives, where we have generally pretty good global coverage for a lot of these different sensors. And that global coverage is matched with a large period of time that we can use for analysis. Oftentimes, these satellites are multispectral. So that means they can pick up on a wider range of the electromagnetic spectrum. However, there are some disadvantages to, say, satellite imagery. One is that, they're lower resolution than some of the other sensor types that we see here. That said, we still have some pretty high resolution satellite imagery out there, which we'll showcase a bit later. Another negative is that they're affected by weather. So if we have a pretty serious cloud cover over an area, that might affect what we're able to measure on the Earth's surface. Drones, on the other hand, provide very high resolution imagery. Pretty much anyone can fly one of these things. If they've got a few $100, they'll be able to capture this high resolution imagery and create high resolution information products from that. And they're not really affected by weather. So you can fly them under cloud cover, for example. You might have to do some normalization for the different weather that you're experiencing, but you're still going to be able to measure those frequencies that are coming from the Earth. However, one of the things about drones that's a disadvantage is that you're limited in the area that you can capture. Theoretically, you could send up a whole fleet of these things and record over a large area, but then we get into issues of data constraints. And that kind of brings me to my next point. We have a lot of different sensors out there. That means there's a lot of data for us to use. So this can be a good thing or a bad thing. When we think about Landsat, there's over 7 million scenes right now. On some days, we're capturing terabytes of data. I think the whole catalog back to 1972 is about 4,600 terabytes at this point. When we look at drone imagery, as I mentioned earlier, that they're pretty much everywhere. That it's very accessible, and as I said, we can capture really high resolution imagery. However, we run into issues of data storage and processing, getting insight from that data. I think if we were to compare one drone image, a mosaic like we see here, compared to a single Landsat scene, it would take about 40 terabytes of data to store imagery for that single Landsat scene. So we have a lot of different sensor options out there. We have a tremendous amount of data, and when we're thinking about it in the monitoring and evaluation context, manual exploitation of this data might be more cost effective than, say, sending someone out to observe or to take surveys, right? But really, if we're going to harness the full potential of this data, we need to develop new ways to develop insights from that. And that's where we get into the realm of artificial intelligence and machine learning. And specifically, when we're talking about remote sensing, we're really focusing in on one section of artificial intelligence, that's of perception, and specifically machine learning. And with remote sensing, it's actually something that practitioners have been doing for years and years, right? When we think of supervised learning classifications, that idea where an individual takes a subset of data and applies a classification to it, then feeds that training sample to an algorithm that can then apply that training sample, the knowledge gained from that training sample, to a larger set of data to create those classifications. That's supervised learning. That's something we've been doing in the remote sensing space for a very long time. But there are other ways, there are other algorithms out there outside of just classification, right, from that supervised classification. Some of the other categories of machine learning are prediction, right? So we think of prediction as deriving information about unknown values from known values. So we can think about certain forms of interpolation, right? Aerial interpolation. Also, we have another type of clustering algorithms, right? So this is the idea where we can train an algorithm to look at a larger data set and identify patterns or trends, whether those patterns or trends are spatial or whether they're temporal. So all three of these are pretty powerful categories. All of them are actually available. All these different types of machine learning algorithms are available directly in ArcGIS already. So if we break down some of those different types, when we look at classification, we're going to see later in our demonstration the use of support vector machine for one of those classification workflows. We'll also see an example of clustering where we look at emerging hotspot analysis and space-time pattern mining. So that's a pretty popular one that we've seen implemented across different industries. We'll show you an example in the monitoring evaluation space. And then the prediction algorithms, when we're looking at spatial regression or the aerial interpolation, as I mentioned earlier. So all of these tools, as we know them as GIS practitioners, are available in ArcGIS already. But there's also been a lot of advances outside of what's currently available in ArcGIS. There's a number of different machine learning frameworks out there that leverage things like convolutional neural networks and these deep learning libraries. And through the APIs that exist on our own end, as well as the APIs for those other machine learning frameworks, we're able to take our geospatial information, in this case remote sensing, and package it up with tools that are available in ArcGIS and bring them to those external frameworks, and then in turn ingest the results as they get back. And we'll show you an example of that in just a minute. So let's take a look at a few use cases of how we might use remote sensing and machine learning. The first example we're going to look at is a situation where we might have a program or a project, an intervention in a given community, and we want to understand whether our intervention there is actually having an impact on the economy there. And one of the proxies that we can use for economic development is actually this transition, this change from thatch roofed houses to tin roof houses. So what we can do is take our multispectral high resolution imagery. So here we're looking at some Digital Globe Worldview 3 imagery that has 8 bands, and we're going to dig into this example in a little bit, but I just wanted to explain it at a high level. Then we're able to leverage the different band combinations in that multispectral imagery and use a supervised support vector machines algorithm to generate a classification for those tin roofed areas, the pixels that are representing tin roofs, and then export building footprints. So this is really powerful because we can look at an area of about 100 hectares in a matter of seconds once we've generated the workflow for training the algorithm. So it's really powerful in that we can cover large areas in a very little amount of time, and we get pretty accurate representation of that indicator of thatch roof to tin roof. Another example that we'll take a look at is an example where we can look at a very large global coverage data set that's at about 30-meter resolution. And this is, I think it's an index that was created from open Landsat imagery. And with that imagery, what we're able to do is get an indication of land cover change over time. So we can see in the animation to the left, we start off from a period of about 2000 to 2014, and we can see the cumulative forest loss over a given area. So this is an important data point, but what does it mean? I think we all probably understand that there's a general trend to deforestation in the world, but we don't really get any focused insights that might help us change our intervention strategy. So what we can do is actually use our clustering tools. So we can take a look at forest change through space and time and have a look at whether there are any patterns there, any trends of continued forest loss or possibly emerging forest loss, or in some cases, maybe diminishing forest loss. What's great about this is that we get this insight for the entire world. So we can apply this to on a global scale, but also if we're working in a particular area, I know 30-meter resolution is pretty good, and we're able to get a sense of what's going on in the specific area and measure whether our intervention or program that might be addressing these issues is effective or not. So the last use case that I wanted to show before we get into a demonstration of some of these tools is this instance of looking at an agricultural development use case. Here we have a high resolution aerial imagery that looks at a coconut grove. Okay, I think this covers an area of about 280 hectares. Through an external convolutional neural network with fast AI, we can feed in our coconut grove aerial imagery, and we're able through training the algorithm to extract specific locations for palm trees. Now this is important because once we have those specific identified locations, then we're able to take a more traditional vegetation indice analysis workflow, or NDVI, on that high resolution imagery, and we can overlay it with those locations. And what we do from there is we get an indication of vegetation health for each of those coconut trees that we've identified the location. So this is really revolutionary. We get an idea of tree health over an area of 280 hectares, and we're not really sending anyone into the field to make these observations. So this is completely recorded without any human intervention outside of collecting the aerial imagery. So you can envision how this might be applied to other use cases, maybe other agricultural crops, or maybe other fields like economic development, etc. So rather than keep talking about machine learning and remote sensing, why don't we dig into a few examples of how this might be applied. All right. The first example I wanted to show you is really just a pure remote sensing example. So we're not going to get into the machine learning algorithms yet. I just wanted to show you some of the ability to differentiate between different features through using time series of imagery. Right. So here we've got a study area of Timbuktu, and I've just got a simple web app where I've embedded these different imagery layers. So I've got some bookmarks, and then here's my layer list. I've got polygons for my areas of interest in Timbuktu. And then I also have a layer from 2014 and 2016. Again, this is, I think it's about 1 meter resolution imagery or 3 meter resolution imagery from Digital Globe. Now, I can take a look at something like the airport in Timbuktu. And here we've got our 2014 layer on top. And I can use my swipe tool, but I kind of like to use the transparency for my layer as a way to show change. So as I make my top layer for 2014 more transparent, we can see that there's development that's been going on. So if we go back to 2014, we have an area of tree coverage and just bare earth. And then if we go back to 2016, we can see that there is clearly some development that's been going on there. So right here we have the ability, without really going into the field, to understand whether large projects are being completed or the progress of them. But this is kind of an extreme example where things are easily detectable. However, if we go to the main road, so this is another area that was being developed. We go back to our 2014 layer. We can zoom in, and we can see kind of areas of pavement and then of bare earth. But then if we were to look at our 2016 layer, we can see clearly that the road is widened and it's a little bit more defined along the lines there. And we can see that this laterite pavement, this red pavement, has a really strong spectral signature, at least in the visible spectrum. So visibly we can see this, but you can imagine what we could do with, say, a machine learning algorithm, where we might identify the spectral signature for this laterite pavement and then train it, and then take those training samples, feed it in the algorithm, and get an idea of the overall roadway health for a given area. Okay, so that's pretty powerful. The next example I want to show you is in Dar es Salaam. And what we have here is an example of how we can leverage remote sensing with some of our existing monitoring and evaluation workflows, right? So when we think of some of our traditional monitoring evaluation workflows, we're thinking of sending individuals into the field to collect information, health surveys, demographic surveys, things like that. So the whole purpose behind this presentation is not to say that remote sensing is going to displace those existing workflows, but rather it's going to help us complement those workflows with a new information stream. So I can open up my bookmarks once again and zoom in to this Mbeze region. I can zoom in a little bit. And here we can see I have really high resolution drone imagery that's been flown after a flooding event. Okay. I also have, let's see here, my layer list. I also have OpenStreetMap data for building footprints. And we can see when I add this OpenStreetMap layer, it comes in, there we go, that there's clearly buildings that have been taken out by this flooding event. And if I were to turn off my drone imagery layer, we can confirm from the imagery base map that we have in ArcGIS Online that there were indeed buildings there before. What I can do is take my damage assessment layer. So traditionally we might send someone into the field to collect these points, right? To say, okay, this building is destroyed or is inaccessible, or maybe has experienced minor damage. But now we can complement that workflow by exploiting high resolution satellite imagery as well. So for example, I can go in and I know that this building that's in the middle of this river is completely destroyed. So I add a point onto the map. I can add in the attribute information, and then that's reflected in my data layer, which again can be pulled into a mobile application. So if I'm out in the field in this neighborhood, I can see that this building has already been assessed and move on to another location. Okay, so again, this is that idea of kind of pure remote sensing being used with traditional field collection workflows, but not really getting into the machine learning aspect of it, or even really remote sensing analysis. It's just using the imagery raw. And already it's tremendously effective. But let's move into an example of how we can leverage machine learning algorithms to gain insight about data sets that are collected from satellite platforms. So here we're taking a look at an investigation, a research project that was performed by Esri, Global Forest Watch, Blue Raster, and the University of Maryland. And what they're doing is they're taking satellite imagery, right? And we saw this earlier in the animation. We see this animation where we're looking at that satellite imagery, creating the forest loss index, and we have that data going through time. But again, what does it mean? What insight can we gain from this? Well, if we use a clustering tool, our emerging hotspot tool, we're able to look at those events through space and time and identify patterns. So initially, we can take a look at those visual patterns. See, it's not loading. Let's go back, refresh. We're going to take a look at those patterns visually through a space-time cube, a 3D rendering of those events. Here we go. There we go. Here it's coming in. So here we're looking at the east coast of Brazil. And if I explore, we can zoom in and see that the forest loss is being grouped by space, but also through time, as we can see in this stack. And certain areas experience persistent forest loss over time, while others might be experiencing diminishing forest loss. Okay, so the forest canopy is remaining intact. So we can take a look at this for a few different geographic areas. Again, this is a global analysis, but we can apply it at a local scale. So the first example we're going to look at is in Brazil. So here in Brazil, we can see our map of just forest loss over that 14-year period, but then that's represented in pink. But the areas in gold actually represent those persistent areas of forest loss. The light yellow areas here represent diminishing forest loss for those given areas. Now, if we overlay other GIS layers like the Amazon biome extent, we can see that although there are persisting hotspots in the Amazon biome, there are significant areas that are experiencing diminishing forest loss, and that can be attributed to some environmental policies that were implemented by the Brazilian government. However, as we mentioned, we have full coverage for this analysis. We can see that there are new hotspots that are emerging outside of that area, as well as intensifying hotspots. So hotspots that are or areas of forest loss which are increasing, and that's taking place in a new biome, the Cerrado biome. So what we can do with this information is we can understand that, okay, our policy that we've implemented to protect the Amazon is working, or there is some progress being made, but it had this other effect of increasing and new hotspots outside of the area, and it can help us change our course and hopefully implement policies that won't just pass the buck onto another geographic area. Okay, so that's an example of using global data sets that were derived from remotely sensed data and applying clustering algorithms to get information about the interventions, in this case at a national scale. Okay, so let's transfer into how we might do some of these analyses, right? So we've seen examples right now of just looking at or exploiting remotely sensed imagery, whether it's satellite imagery or drone imagery in the case of Dar es Salaam. But how do we actually perform some of these machine learning algorithms? How do we exploit this imagery at scale rather than just taking a look at it and using it that way? So in order to demonstrate this, we're going to look in ArcGIS Pro. And I've got a Pro project that has some, again, Digital Globe Worldview 3 satellite imagery. So what we're looking here is actually a multispectral image that covers coastal, blue, green, yellow, red, red edge, near infrared, and 2 bands of near infrared. So it's 8 banded. So if we look at this, Let's see, let's zoom into a particular area of interest. Okay, we can see it's pretty good resolution. It's not super fine, but we can distinguish features. We do have a pan sharpen band pan sharpen view that uses that black and white merge with the multispectral to give us a little bit of a crisp image. But we're really going to work with the multispectral data layer here. We can always go back to the pan sharpened image if we want to say trace objects for spectral profiles and things like that. I just want to show you how you can use this multispectral image to get a bit of information. So what we can do is use some of the charting tools that are available. By right-clicking the data layer and selecting Create Chart, I can easily make these histograms. So this is going to give us a distribution of the different pixel values for a given band across the entire image, right? So for my first histogram, I want to take a look at my second band. Okay, so my second band represents blue. And here we can see that it's pretty narrow, the distribution. We can see that when we get to about 2000, so 2000 as a value that's being reflected, we see a really long tail. So there's not a lot of pixels that are reflecting at that level. So if we add another histogram for a different band, let's take a look at the third band. So here we can see a pretty similar spectral profile. We have a lot of pixels that are really concentrated around this mean value for both of them. So we have about 1300 for our third band, which is our green band, and then we have a little bit over about 1100 for our second band, which is our blue band. But if we were to take a look at, say, the fifth band that we're showing, which is our red band, so we have our red, green, and blue, our natural color, we can see that the distribution's a bit wider. So the mean is much higher, and we have, a smaller tail, relatively smaller tail as compared to 2 and 3. So with this histogram, we can see that most likely there's some sort of correlation between bands 3 and 2 that we can possibly exploit. So in order to take a look at that, we can actually take a look at another charting type, which is called a scatter plot. So with our scatter plot, we're able to plot our values on an X and Y axis. So here we can take a look at our second band, because remember we think there's some correlation there, in our third band. And what's great about this is the chart is completely interactive. So remember we had that tail that started around 2000. Well, if we select the values, these are all pixel values on our chart that are over 2000, we can see that a pattern emerges, right? These areas of blue seem to correlate with our tin roofs. And I should say this is that example that we showed earlier, backing up a little bit, where we're looking at the difference between thatched roofs and say tin roofs. So this is important for us. We're able to use the fact that there are very few values in this spectral range to exploit that imagery. Okay. So why don't we use another one of our tools, which is the spectral profile chart. And in order to use the spectral profile chart, we need to generate some areas of interest that will return average values over that spectral range. So if we take a look at our image here, let's focus maybe on vegetation and this tin roof. We can define our area interest by just drawing on the image. And we can change the way that that's visualized in our profile. And then we can define other areas of interest. And this allows us to take a look at those spectral profiles. So here we've got our vegetation profile 1 and our tin roof. We can see that there's a very different profile. So I've got one of these already baked up. So let's take a look at that. So here, this is that same spectral profile, spectral signature graph that we had seen earlier in our slide presentation. So the different colors correspond to the different areas on the map. So we have our tin roof, our metal roof that's coming here on the blue line. And we have vegetation represented in green, and then thatched roof and bare earth represented here in brown. I think the important thing to take away from this this graph of the spectral signatures is the areas where they're different, right? So we can see in band 2, for example, we have a pretty big difference between our tin roof, our bare earth, our thatch roof, and our vegetation. Something happens similarly at band 5, where vegetation, our thatch roof, our tin roof, and bare earth are different. And then again, we get that separation on band 8. So band 8, 5, and 2 are opportunities for us to distinguish between these different physical characteristics that we see in our image. So why don't we explore some of the band combinations to illustrate this point? Let's go back to my content pane. And if I look at my image, I'll zoom out a little bit. I can go in and manipulate the different band combinations for this image. So right now we're looking at red represented by band 5, green represented by band 2, and blue represented by green band 3 and blue band 2. But I can look at these different band combinations, and they're going to give me different representations of my data. So here I have 4, 5, and 8. If I look at my flooding band combination, 6, 7, 8. But remember, we had said that 8, 5, and 2 were really those areas that we thought that we would get some distinction between the different pixel values in our image. So I have a band combination already baked, and we can see that where our tin roofs here in yellow stand out much more, or there's a high degree of variance between the tin roofs in yellow than the vegetation in blue, and then the purple shades that represent our thatched roof and our bare earth. And we can use this band combination to feed into our classification algorithm to generate building footprints for those tin roofs. Okay, the way we would do that is by going into our imagery tools and using the classification wizard. Now I'm going to zoom into an area of interest because one section of this demonstration will use on-the-fly processing. So if I zoom in to an area, I can see that I'm going to use this classification method, the supervised classification method that I was mentioning earlier. I want it to be object-based rather than pixel-based because I have objects, right? I have my tin roof, my vegetation, so it's these groups of neighboring pixels. I can use my classification schema that I've already created. I'm just going to use a schema that has 3 classes, one for metal roofs, one for vegetation, and one for bare earth. And then I can also incorporate training samples into this classification wizard. So I've got a shape file with a few points there, and I can move on. Now, the first step in performing this image classification is to segment my image into different groups, right? So there's different variables that we can select here. The spectral detail is going to determine the number of different classifications that we're after. From experience, I know that 14 works well for this image. And then the spatial detail is going to let us know, or it's going to determine how smooth that segmentation is, whether it's going to be very rigid if it has high spatial detail or a little bit wavier or smoother with the lower spatial detail. And when I show the segment boundaries, that's going to allow me to select the different segments and classify them into my classification scheme. So this is going to take just a minute while it processes. What it's doing is looking at the area of extent here for my image, and it's processing the algorithms, or sorry, the pixels into different segments. Okay, and maybe this was a mistake in demoing. There it goes, it's starting to go. It'll take just a minute, and what we'll see is these little wavy lines around groups of pixels. They won't be specific to the vegetation outline or the tin roof outline, but what they will do is group to smaller groups, or they'll cluster to smaller groups, as you can see here. The classification algorithm is actually what's being used afterwards in order to get those finer groups. So in order to train the algorithm, I need to select some of these segments. So if I click on vegetation, for example, and I know that blue is representing my vegetation, I can click on an area. And disclaimer, the first time you click on the image, it takes a little bit to process. But as soon as you've done that first selection of your segments, then it goes very quickly. You can very rapidly select the different segments that are going to train the algorithm. So just give it 1 minute to complete. We can see that the segments roughly align with the objects that we want to classify. Okay, here we can see that we've got our first segment selected, and then we can go through and select any number of these. The larger the number, the better, of course, and we can group these so that they represent our 3 different classes. Okay. So I'm gonna end the actual workflow here. The next step would be just to run the supervised classification using the support vector machines algorithm. But I'm going to just exit out of this tool and show you the results of that algorithm. So what we can see here, let's see, no, it's not showing up. Let's see here. Okay, so let me go back here. We're looking at the metal roofs, so let's do that in blue. Let's do vegetation in dark green, and other is not showing up. Okay, so what you should be seeing here is an image that's divided into 3 different pixel types. When I had worked out with it earlier, the tin roofs were gray, the vegetation areas were green, and then everything else was this purple color. I assure you it works, it's just not visualizing right now. But what we get after we run that algorithm is the rough areas for those different classification types. But then we can take our tin roof pixel type that we can see here in yellow and actually run a tool to generate the building footprints. So in the end, what we're seeing, if we look at our pan sharpened image, is a pretty good estimation for the building footprints for the satellite image that we captured, or that we ran the analysis on. And importantly, with these building footprints, we can actually look at the attribute table and get an idea of the total area for each of those footprints. Okay, so you can envision applying this to multiple areas. We get an idea of the size of the tin roofs that are there, and then applying that algorithm or that workflow to multiple images through time, and we get a sense of change in the size of the building footprints. Okay, so that is all I really wanted to show you from a demo perspective. One thing I guess to add here is that you can also run accuracy assessments on this using random points. And I think for this particular analysis, we were right at about 93 to 94% accuracy. So that's pretty good. We're looking at over 100 hectares of area here, and we're able to identify these areas of the tin roofs. And again, that's a proxy for our economic development. Okay, so why don't we move back to some summary thoughts, and then we can hopefully get into some questions and answers if you've been populating those in the chat. So the whole point behind this webinar and the presentation is that with remote sensing and machine learning, as it's applied to monitoring evaluation, we are really getting an increase in the amount of information that we're able to use. Again, I said that we're not trying to displace existing M&E techniques or methodologies. We're really looking at remote sensing and machine learning as another tool that can augment existing workflows. And we think there's a real opportunity to improve, to decrease the time to information by using some of these sensing techniques and algorithms, and hopefully can reduce the amount of resources needed in order to capture information for a given area of intervention. And ultimately, with a decrease in time and resources, better information, ultimately what we're really looking at is improved results for your programs, for your interventions. That's what the end goal is, and hopefully with some of these techniques, we can get there. All right, so let's take a look at some of the questions we have here. Okay, give me a minute. In the chat. Okay, so I have a question here about, let me go to the top of the list. So one of the questions is kind of a logistics question, and it is, will the webinar be available? Will the slides be available after the webinar? The answer is absolutely. We will both, this webinar has been recorded, so we will actually post a recording of the webinar on YouTube. So if you have any colleagues that were not able to join us, then we can certainly share out the link to that YouTube video. And we will also send out a PDF version of the slides that were presented here. So we can definitely share that out after the webinar. Okay. So we have some questions about imagery type, GeoTIFFs, NITF, and whether the support vector machines algorithm, whether the type of imagery impacts the support vector machine algorithms. To my knowledge, any of the imagery that's supported in ArcGIS Pro in this example should work with the support vector machines tool. I would just say to point you to the documentation for the tool. The documentation is generally very thorough and gives you a great overview of the tool and the different inputs that are valid. That said, if you have any further questions regarding the tool, there's always Esri technical support. We have specialists that are very familiar with the tool, and if you're having issues there, don't hesitate to contact me. My email is at the beginning of the slide. I probably should have put it on this slide, but it's boneil@esri.com. Okay. So there's a question about, are there any open source drone images specifically for Nepal? That's a good question. Through the ArcGIS platform, we host a number of satellite imagery catalogs. So you can get access to the entire Landsat catalog available as a service that you can use directly in ArcGIS Pro or in ArcGIS Online or ArcGIS Enterprise, any of the tools. So that's available, the whole catalog back to 72. We also had the Sentinel-2 catalog available on an 18-month rolling archive. So from any given date, when you're accessing the imagery, you have about a year and a half of the imagery prior that you can access directly as a service. And then, of course, there's the options for the kind of traditional option for downloading, extracting, and loading it into the platform. As far as aerial imagery, I'm not sure. I mean, we work with a number of partners that are working on programs. For example, I know with the Rohingya crisis that's going on in Cox's Bazar in Bangladesh, there are a number of different drone imagery layers that are available that you can bring into different parts of the platform. But as far as a overall landing place or platform for imagery for different areas, we don't have that yet. But I think that's a great idea. I'd be very interested if there are people out there that are interested in kind of generating a community. From a technological perspective, it's very easy to set up the hosting environment for the imagery, and we'd be happy to host it. We just need to collect it and to disseminate it. So feel free to follow up with me after, and I'd love to discuss that with you. Okay. Let's see. So one question is specific to desktop. So for those of you out there, we have ArcGIS Desktop is the product, and then we have two tools within it. One is ArcMap and one is ArcGIS Pro. I'm sure there's a whole bunch of you out there that are more familiar with ArcMap, but ArcGIS Pro is really the desktop application that we're investing all of our innovation in, and there's a lot of new tools. So one of the tools that is incorporated in ArcGIS Pro is that image classification wizard. So I think from a feature equivalency perspective, and I don't have the documentation offhand, but I think we're probably similar as far as the disparate or the disconnected image classification tools. But what ArcGIS Pro has is the nice workflow with the wizard that kind of steps you through the different tools that you need, whether it's the segmentation piece and then the classification piece, and then finally the accuracy assessment afterwards. So Pro kind of gives you a more streamlined workflow that connects the dots between these different tools. Okay, the question is, do developers have access to all the tools? What are the limitations for developers? That's a really good question. So the tools that are available in the GUI or in the desktop, yeah, those are all accessible through APIs. You can build your own custom runtime applications with the runtime SDK, but you can also access the different analytical libraries specifically through the Python API is a great way of doing that. I really like the kind of pattern of using Jupyter notebooks to connect to the different imagery processing tools available in ArcGIS Pro through that Python API. So that's a great resource there if you're doing a little bit more command line stuff or building your own applications. A lot of the imagery tools as well can be shared as services to the web environment. So at that point, through the JavaScript API, you could build your own custom applications that reference those analytical services. A great example of imagery applications, and maybe I'll just show it to you. I think that makes sense. Is this Landsat Explorer? So what it does is it takes the Landsat catalog that I mentioned earlier, and it exposes not only the imagery, but a number of tools in a pretty simple interface. So here, for example, we can look at, we can compare different segments of time. We're looking at Redlands, California. So we can look back at scenes in history, and they load pretty quick. We can kind of grab those scenes and then we can create, so that's probably a bad scene to show, it's got some cloud cover. So we've got that selector, that's a bad scene too because it's split. We're able to we can just look at this area here. So we're looking at the two areas in time, but then we can expose tools, like for example, these change detection tools where, maybe we're looking at vegetation indice or maybe the urban index to give an indication of growth over time. So we can look at just a pure difference image where we're looking at purple as loss and green as gained. But then we can also use this difference mask, which I think is a really cool tool, where here we can adjust our mask values for negative change or positive change, and we're able to adjust the transparency on there and even take a look at our swipe tool, where we can compare the images over top of each other. So this is an example where we're taking some of those analytical tools like the masking, we're exposing them as services, and then we're wrapping an application around that allows us to interactively exploit the imagery, and it's a really nice analytical information product, I'd say. So to answer you, the SDK to build your own runtime applications, the Python API is great for kind of analytical workflows. Jupyter notebooks are great for that. And then you can also expose the imagery and analytical tools. I didn't really show you raster functions, but as raster functions, that then you can wrap different applications around. Okay. This is a good question. It has to do with maybe some of the agricultural workflows. And it's saying, assuming I have a very high resolution imagery, would I be able to differentiate between species? So I think the answer to that is maybe. Vegetation has different types of vegetation have different types of spectral signatures, and there's patterns across them, and sometimes it's easy to distinguish with manual exploitation. And I think probably as the machine learning algorithms evolve and get better, and we have better training data, that we probably will get to the point of good of being able to distinguish between species for say land cover analysis and things like that. And I'm sure some of that is going on right now. I personally haven't seen a really robust case of kind of differentiating between species. You might be able to do between like cropland and things like that and trees, but say between corn and soya, I haven't seen it. I'm not an agricultural economist with remote sensing specialty, but I think there could be challenges there. That said, one of the things that we can look at is actually using machine algorithms to look at patterns and then comparing yields and things like that, especially if we have consistent crop cover over time, and then comparing those predicted yields to actual yields, and getting an indication of intervention strategies and things like that. So I think that's definitely possible with the species differentiation. I haven't seen it, but I would encourage you to maybe look more at the academic research papers and things like that. Okay, so I think we have time for one more. Let's see, I'm looking through here. So one of the questions is, so the costs of acquiring this imagery. So as I said, some of the government-funded space programs and things like that, ESA and others, make these imagery catalogs available to the public. Others are available through commercial providers, right? Some of the higher resolution things, which incur a certain cost. However, in our space, in kind of the nonprofit global organization space, there are special licenses available for organizations that are, promoting conservation, working in humanitarian aid, et cetera. So I would encourage to look on look on the internet for some of those deals, some of those agreements where you might be able to have access to pretty recent imagery at either drastically reduced costs or no cost at all. So that's about all the time we have today. There's a number of different questions that are great that I was kind of flipping through, but we didn't have time to get to. I'll do my best to take a look at them and get back to you and email you with some answers. Again, if you have any questions, please reach out to me. Boneil@esri.com. BONEILL@esri.com is my email address, and you can get me at Twitter @geo_Neil. Thanks a bunch for your attention, and I'm looking forward to seeing great examples that are coming out of our user community soon.